Hey, it's Mr. Allred, and I'm going to work out a problem I gave you. Looks like it may be a little bit harder getting started depending on your resources, but we're trying to find the area enclosed between two curves, y equals x to the fourth and y equals 8x. Now, if you have a grapher, like a graphing calculator, you can kind of figure out this region pretty quick. Or if you want to make a table, this one's pretty nice and you could figure out the region also pretty quick that way. Neither one of these is hard to graph, but you kind of want to hit the right points. If you don't have a grapher, one thing you could do, because you got to figure out where they intersect. Okay, you got to figure out when you build your integration what those endpoints are going to be. So one way you can do that is set the two equations equal to each other. So in that case, when you have the same x plugged in, you're looking to get the same y since both of these are equal to y. Now, in solving this, it's going to draw on some pretty old material that you probably haven't used in a while, but you'll bring everything over to one side. So we got x to the fourth equals 8x, and then when we bring that over, we can factor out an x. Okay, and in this case right here, what you see is you got x times x cubed minus 8. So you can set this up as x equals 0, and you can set up x cubed minus 8 equals 0. You could use a cubed factoring formula there, but it'll probably just be easier if we just go ahead and bring that 8 over and take the cube root and get x equals 2. So we've got these two places where the graphs would intersect. So when we do that, we're going to be running this thing from 0 to 2. Now the next thing we got to do is figure out which one is on top, and we haven't graphed them. So if these are the only two places they intersect, 0 and 2, then we should be able to pick a point in between there and figure out which one's on top. So if I let x equal 1, what do we get? We would say y equals 1 to the fourth is 1. Okay, so the first one would have the point 1, 1. So we know it has a height of 1 there. And the second one, y equals 8 times 1, is 8. So basically what that tells us, when x is 1, the y value is bigger for the second one. So the second graph is the one that's on top. Okay, 8x would be the top layer, and then minus x to the fourth would be the bottom layer, and that'll be dx. I don't know that I can graph it very well. But x to the fourth looks kind of like x squared. Let's undo that. Got a little too steep. But it looks kind of like x squared, like that. And 8x looks like a straight line like this. So I haven't put anything in there. But this point right here must be x of 2. And if you want to figure that out, you could plug 2 into both of these and see it would give you 16, although that 16 really doesn't matter. And then the other place to intersect is down here at 0, 0. So what we're doing is we're finding this little shaded region in between here. And the straight line, which was the y equals 8x, is the top one, and the parabola looking thing, the y equals x to the fourth, is the bottom one. So like I said, you got to figure out which one's on top. You can do that by graphing them or calculating points possibly, and you also have to figure out where they intersect. Once you have that, the problem becomes very, very easy. So let's go through it. So we've got the integral from 0 to 2 of 8x minus x to the fourth dx. So we're going to integrate antiderivative. So this goes up to x squared divided by 2, so it'll be 4x squared. The other one will go up to x to the fifth divided by the 5, so it would be minus 1/5 x to the fifth. And that would be from 0 to 2. So now we want to plug in the 2. So we'll have 4 times 2 squared, which would be 4, minus 1/5 times 2 to the fifth, which would be 32. And then we'll have minus when we plug 0 in. So 4 times 0 minus 1/5 times 0. So this whole last part just zeroes out for whatever reason. What we have over here is we have 16 minus 32 fifths. I guess we have to put these in like denominators. So 80 fifths is the same thing as 16 minus 32 fifths. So that takes it down to, what, 48 fifths, I believe? Yeah. So hopefully that's our answer. So I didn't make the region look very big there just because of the way it is. But what is that? That's about an area of 10 units, 48 fifths. So you have to imagine this thing being really stretched up, going all the way up to 16, and there being a pretty big or pretty wide gap in there for a little while. Actually seeing it mapped out would probably be a little bit better. Let me pause the video and see if I can pull up on Desmos just in case you're curious. Okay, so I'm back here. I just pulled this on Desmos to show you whether our graph looks accurate. It intersects down here at 0, 0 and over here at 2, 16. And it looks for a long time like this space in here is about 1 wide. So 1, 2, 3, 4, 5, 6, 7, and then it starts to get smaller. So it seems like it could be somewhere between 9 and 10 units in there possibly. But you don't really need that to check yourself. It just kind of helps you feel a little bit better if you could have the graph. But because it goes up so high in such a short span, it's really kind of hard to get it on there looking very nice. All right, thank you.